Alright everyone, here's the next video. I know I said I was going to pick up with that other problem, but I decided to put that away in favor of moving to the next kinematic equation. So we're going to learn another kinematic equation, then see a practice problem with it, and then we'll move on from there. So the next kinematic equation that we're going to work with is an equation that allows us to find displacement under a constant acceleration. So that requires the following pieces of information. So the formula itself is delta x equals vi, v initial, delta t, so the initial velocity times the time, plus 1/2 of the acceleration times the change in time squared. And it's very important that only the time is squared. Okay? So if we want to find displacement, what we're going to need is the initial velocity, its acceleration, and how much time how much time it takes to go from the initial velocity to its final velocity. So this comes from our two previous kinematic equations. It comes from the delta x equals 1/2 vi plus vf delta t, and the vf equals vi plus a delta t using substitution. I'm not going to do that derivation for you because it's a little bit complicated and it's not something that you need to know. What you do need to know is when we look at this new formula, we have vi times delta t. This delta t squared is its own little unit multiplied by a multiplied by 1/2. So remember, only square the time. All right. So let's go ahead and use this. A car accelerates at a constant rate of 2 meters per second squared, starting at 15 meters per second. So we are beginning our stopwatch, essentially, when the car is already going 15 meters per second. So if we have a rate of 2 meters per second squared, starting at an initial velocity of 15 meters per second, and we do that for 1.5 seconds, how far does the car travel in this time? So let's pull the information out that we might need. We accelerate at a constant rate of 2 meters per second squared. We start at a VI of 15 meters per second, and we do that for a time of 1.5 seconds. Finally, we are asked to find how far, meaning displacement. That is our unknown. So we've got all the information that we might need. Now let's pull together some formulas and solve. So we could skip this step because we just learned a new formula, so you could assume we're going to use it, but it's good practice to list everything regardless. So let's do that. So what do we know? We know that v equals delta x over delta t. We know that a equals delta v over delta t. We know that delta x equals 1/2 vi plus vf delta t. We have our vf equals vi plus a delta t. And now we have delta x equals vi delta t plus 1/2 a delta t squared. So let's do our sanity checks and see which formula we should use. Let's decide which one of these is going to be the best. So first of all, v equals delta x over delta t. That's only for a constant velocity. We are not under a constant velocity, so that's out. A equals delta v over delta t does not contain delta x, which is what we're trying to find, so that's out. All right, let's look at the next one. Delta x. Ooh, we're looking for that. That's good. 1/2 is a number. Vi we have. Vf we do not have. We do have delta t, but we don't have everything we need, so this one's out. The next formula, Vf equals Vi plus a delta t, does not contain delta x, therefore it is also out. So we're left with one final formula. Let's just make sure we have everything we need. Vi, yes. Delta t, yes. A, yes. Delta t again, we still have it. And it solves for delta x, which is what we want, so we're going to go ahead and move forward with this formula. So let's write it down one more time before we fill it in. Delta x equals vi delta t plus 1/2 a delta t squared. All right, delta x is our unknown. Vi, 15, delta t, 1.5, plus 1/2 a, 2, delta t, 1.5 squared. Let's start working our way through this. So our delta x equals 15 times 1.5 gives us 22.5 plus a 1/2, 1/2 of 2 is 1, and 1.5 squared is 2.25. So what we're left with is delta x equals 22.5 plus 1/2, 1 times 2.25 is just 2.25. And then we add those together. We end up with a delta x of 24.75 meters. Have we answered the question? Yes, we have. All right, very good. Moving forward, the last kinematic equation is typically, I see for students, the easiest, at the very least, to determine when to use it. It does contain 2 squares, so 2 powers of 2, but that's not particularly complicated if you know how to take square roots and or square numbers. The reason why it's the easiest to determine when to use it is because it is the only kinematic equation that does not have time. So when time is not given, you can still figure out some of the characteristics of motion of the object. This derivation is not particularly easy. I will not do this derivation either. But it does come from the previous equations just kind of shoved together and jumbled around. But this equation says Vf squared, so the final velocity squared, equals Vi squared, initial velocity squared, plus 2 times a acceleration times delta x displacement. So Vf squared equals Vi squared plus 2a delta x. Notice that time is not present at all. As long as you know 3 out of the 4 pieces of information here, you can solve for whatever you might want. So let's go ahead and move forward with this equation. So here's an example. An ostrich is accelerating from rest at 0.5 meters per second squared. If the ostrich travels 4.75 meters, what is its final velocity? So we're not provided with time, which is kind of a dead giveaway as to what formula we're going to use. But regardless, let's go ahead and write down some stuff. So we are accelerating from rest, meaning Vi is 0 meters per second. That's what rest means. At an acceleration of 0.5 meters per second squared. And we are traveling a displacement of 4.75 meters. We are asked to find the final velocity Vf. That's our unknown. Let's go ahead and list some formulas. We could take the quick step and just decide that, yeah, I know which one I'm going to use. Time is not given, but let's look at them anyways, just for a quick second. Let's say we have our delta x equals Vi delta t plus 1/2 a delta t squared. Let's say we have our Vf equals Vi plus a delta t. And let's go ahead and list our Vf squared equals Vi squared plus 2a delta x. So So let's look at these and let's make sure that we are clear on which one we should use. The first one, delta x we have, yes. Vi we have, but we don't have delta t. We do have a, but we still don't have delta t, so this guy is out. Next one, Vf we want, Vi, okay, looks good. A, oh, and no delta t. So that one's out. Let's make sure we can use our final one. Vf we want, Vi we have, A we have, delta x we have. So let's go ahead and use this guy. So our Vf squared equals our Vi, 0 squared, plus 2, acceleration of 0.5, times our delta x of 4.75 meters. So Vf squared equals 0 squared is 0, so this drops out, plus 2 times 0.5 times 4.75 is 2.375. Okay, so we also could have just said, oh, 2 times 0.5 is 1, but whatever, we went the long way around. So Vf squared equals 2 times 2.375 is indeed 4.75. Now, we might be tempted to say, yay, we're done. But we are not done, because notice we have found Vf squared. So in order for us to finish this problem, we need to get rid of that square with a square root. So Vf equals the square root of 4.75, which is going to be a 2.18 meters per second. And there we go. We have solved the problem. All right. Okay, we're going to end the video here, and we're going to pick up in our next video with graphs of the kinematic equations and the kinematic quantities, not kinematic equations, but things like the displacement versus time, velocity versus time, etc. So we'll pick up there. See you in the next video.